polymorphic encryption.
All right, thank you. So thank you to the organizers for inviting me, and thank you everyone for waking up and coming. So I'll tell you about two-round MPC via multi-key fully homomorphic encryption. This is joint work with Pratyay Mukherjee, who's here in the audience. He's going to be a postdoc here at Berkeley next year. All right, so multi-party computation, we all know what it is. We have some number of parties. They have inputs, x1, x2, x3, and so on. They want to compute some function f applied to these inputs. And they're going to do this by running a protocol. The goal of this protocol is that everyone should get the output, and nothing else about the input should be revealed to the other parties. And here I'm going to assume a setting with many parties and an arbitrary number of corruptions. I'm not assuming honest majority or anything like that. And so this is a question that's been studied since the 80s. For this talk, the main question that we're going to address is what's the minimal round complexity of multi-party computation? Can we construct MPC with the minimal number of rounds? A round just consists of all parties broadcasting a message to all other parties without waiting for each other. Okay, so if Alice and Bob send a message to each other at the same time, that's one round. If Alice sends a message to Bob and then Bob has to respond to it, depending on what he got, that's 2 rounds. Okay, that's how we're counting rounds. So that's the main question, what's the round complexity? Another side question, sort of less quantitative, more qualitative, want to construct MPC directly using FHE techniques without going through things like oblivious transfer and GMW, so sort of a different way of doing it. Okay, so what do we know about round complexity? So ideally, 2 rounds is the best we could hope for. We know we can't do 1 round. On the other hand, if you look at the old protocols, the original GMW, they take many rounds proportional to the circuit size. But it's been known for a while, since the 90s, that you can actually do a constant number of rounds. And I think the constant isn't written anywhere, but if you ask the Oracle, Yuval, he'll tell you it's 4. So we know how to do that from just oblivious transfer. More recently, we know how to do 3 rounds from LWE using fully homomorphic encryption techniques, and even 2 rounds from indistinguishability obfuscation. But the question is, can we do 2 rounds without obfuscation? Can we do it from more standard techniques? And just some caveats, all of these results are in the common random string model. This is actually needed for malicious security. I don't think it's needed for semi-honest, but the results, these 2 results do need it even for semi-honest. And also we require NISX to get malicious security in addition to the assumptions that are here. For semi-honest, we don't need NISX. And so the main result of this talk is I'll show you how to do 2 rounds from learning with errors assumption instead of obfuscation. You can just do it from LWE. Okay, so let's start with a template. How would you do multi-party computation from fully homomorphic encryption? And fully homomorphic encryption seems like this powerful primitive, but it's not clear how to do MPC. Who chooses the key? Well, that's the main thing. Who chooses the key, really, and who decrypts? Okay, so here's an idea for how to do it. In the beginning, the parties will run some sort of a distributed key generation protocol for an FHE schemes, where they somehow agree on a common public key, and they each get a secret share of the secret key in an N out of N secret sharing. Okay, so somehow they do that, and then each party I will just encrypt its input xi under the common public key, broadcast that ciphertext. Once that's done, the parties can homomorphically compute the function. So there's a deterministic procedure. Every party can just do it individually and get the same answer. So get the same ciphertext C star that encrypts the output of the function. And then the parties can run a distributed decryption protocol where they use the shares of the secret key to somehow recover the output in plain text. Okay, so that's the template. How do we actually instantiate this? Well, it turns out that if you use specific fully homomorphic encryption schemes, the one from Brakersky-Vaikunthanathan and Gentry-Sahai-Waters then you can actually directly construct these distributed key generation and decryption protocols with 1 round each. Okay, that's for specific schemes. And then if you instantiate it in this framework, you can get a 3-round multi-party computation protocol. So this is something we showed in a joint work with Asherov, Jain, Lopez-Alt, Tromer, and Vaikunthanathan. Okay, so that lets you do 3-round MPC from LWE. Can we somehow reduce it to 2 rounds? Well, which round should we get rid of? What should we get rid of here? We're going to try to get rid of the first round. Okay, so we're not going to somehow run a distributed key generation. Well, what does that mean? So now each party will just choose its own individual public key secret key pair without coordinating. And it'll just encrypt its input under its own public key and broadcast that ciphertext. And what we want now is to somehow be able to take these ciphertexts that are encrypted under completely different keys, uncoordinated, and somehow still be able to compute on them. And what do we get at the end? Some ciphertext that encrypts the output of the computation, but under all the public keys, right? So no individual party can decrypt it at this point, but this means that somehow it's encrypted in such a way that with all the secret keys together, you could decrypt it. Okay? So this is just one round here. And then the parties will run some sort of a distributed decryption, where you take all the secret keys together, but in a distributed way, and just get the output, just decrypt the output. So what do we know about this primitive, this kind of multi-key fully homomorphic encryption? I mean, it doesn't follow from standard FHE, but it was a notion that was defined by this work of Lopez al Tromer and Vaikunthanathan, and they showed how to construct it using an n-truth type assumption. Okay? So they constructed it, but unfortunately there was no nice distributed decryption. With all the keys together you could decrypt, but there was no nice way to do it in a distributed way. In fact, the way they suggested to do it is to run the 3-round protocol from the previous slide. That was the best way to do a distributed decryption. More recently, there's a paper that showed how to do multi-key FHE from just the learning with error assumption. So there's a paper by Clear and McGoldrick. It's a paper that appeared on ePrint about a year ago. It's been there for a while. And when it first came out, it's an exciting result. I really wanted to understand it. But somehow there's a lot of algebra. I couldn't get through it. Maybe arrogantly, I sort of wasn't really sure if it's something that if there's a real result there. Pratya was visiting me at Northeastern, so I sort of assigned this to him. You know, can you please read this and try to figure it out? And eventually he figured out there's a really good idea there. It took him longer to convince me, but we start simplifying it. And I think by this point, we actually have a simpler version of this that's easier to present, so hopefully I'll be able to present it all to you. So in this work, the main result is first to simplify the multi-key FHE scheme from this work. And then we show how to do a nice one-round distributed decryption procedure for this particular scheme. And plugging it together, we get 2-round MPC. Okay, so this is the main thing I want you to take away, this picture. Now we're going to get our sort of hands dirty and go into the algebra. Yeah?
When you're revealing at the end the output, you don't mind revealing the secret keys or anything?
I do, because then if I reveal the secret keys, then you could decrypt the original input.
In the original paper by Lopez and so forth, when they were revealing, they actually revealed the secret keys. Right,
so that's right. So this notion of multi-key FHE just says you can compute on the ciphertext and get something, but it doesn't say how do you decrypt it. It just says there's a way to decrypt if you have all the secret keys together.
Just revealing the secret keys one by one?
They were. They didn't care about how to decrypt. They weren't using it in the context of MPC. We want to use it in the context of MPC, so we want to decrypt in some distributed way without just revealing the secret keys. That's the difference. So this notion, yeah, I think it's a good thing to emphasize. This notion of multi-key FHE is interesting even if you don't have a nice distributed decryption procedure. But you can't use it for 2-round MPC then. Okay? So we're going to start. I'm going to start by describing the Gentry-Sahai-Waters or GSW fully homomorphic encryption scheme. So Shai described it at the boot camp. I'm going to tell you, just refresh your memory for those that were there. Then I'm going to tell you how to convert it into a multi-key FHE. So this will be a variant of the Clear and McGoldrick result, simplified. And I'll show you how to build 2-round MPC from it, essentially using the template you just saw. OK, so we're going to have to do some algebra. So let's see. So let's start with the key generation. I'm just describing right now a single key FHE scheme, the GSW scheme. So the public key will be a matrix, n by a matrix. The first n-1 rows, uniformly random. I'm going to call that B. And the last row is going to be what's called a learning with error sample. So it's going to be some linear combination of these, so S times B plus some error vector. Okay, that's just the last row of the matrix. And the secret key is a little weird. It's going to be this vector S that denotes the linear combination, negated, and 1 at the end. Why am I doing that? This is the main property. If you take the secret key T multiplied by the public matrix A, you get actually this error vector E, and I'm going to ignore error vectors. They're small, so I'm just going to say, yeah, that's close to 0. Okay, so you get something close to 0. This is the main property to remember. Okay, so how do we encrypt with that? So the encryption will take the public key A, this matrix on the last slide, and just multiply it by some m by m 0, 1 matrix. So matrix with 0, 1 entries. You can think of that as somehow re-randomizing A, and then we're going to add X, this is the bit we're encrypting, times some matrix G, which I'll call a public gadget matrix. I'll tell you what it is in a little bit. Okay, but this is the encryption procedure, and here's the main property you should remember. This is the thing you need to remember for the rest of the talk. If you multiply the ciphertext by the secret key T, then T times A is small, right? It's close to 0. R is small, close to 0, so that sort of cancels out, becomes small, and you get XTG. So you get the bit, the encrypted bit out, multiplied by the secret key in G. Okay? So this also lets you decrypt. Now, if X is 0, this is small. If X is 1, it's big, so you can tell the difference. You can decrypt. Okay, so that's the property. I'll tell you a little more about the gadget matrix. We'll need to use it. I won't actually care too much about what exactly it is. I'll tell you what property it has. That's what you need to know. So the main thing is that there's some efficiently computable function, G inverse. So this is not a matrix inverse. These aren't square matrices. You can't invert them. But we'll sort of cheat, and it'll be mostly like an inverse. So this is a function that takes an n by m matrix as input and outputs a 0, 1 m by m matrix. So matrix with short entries, but bigger matrix. And this property holds. G times G inverse of C is equal to C. So you can sort of just think of this as a matrix inverse and cancel, even though it's not. Okay, those are the main properties. And for those that know, the way to implement this, the G inverse is actually the bit decomposition function. And then G consists of powers of 2. It's a matrix that has powers of 2, 1, 2, 4, 8, and so on. Okay, so now let's see how to do homomorphic operations on this in this scheme. So we have two ciphertexts, C1 and C2. They encrypt bits X1 and X2. So this equation holds for each ciphertext. This is the secret key T. So how do we add? Just add, matrix addition. Okay, so T times T plus is this. You just get X1 plus X2 TG, so you have an encryption of X1 plus X2. Multiplication is more interesting. Here's what we do to multiply. We can't just multiply the matrices. They have different dimensions, but we'll do the next best thing. We'll do C1 times G inverse of C2. Okay, so what's happening here? If you try to decrypt this C times, well, you get TC1, that's XTG, plus some error. I'm going to write the error explicitly here because it's good to keep track of, times G inverse of C2. Now, G inverse of C2 is short. This error is short, so they're sort of going to cancel out, become short. So you really get just X1T times C2, the G and G inverse cancel. And now TC2 is X2TG, so you get this. Okay, so this works out, and then you can do any homomorphic operations you want. So that's it. That's a FHE scheme, 4 slides. You know everything now. So let's try to make it into a multi-key version of the scheme. So here's the scenario. We have n parties, and they have completely independent GSW key pairs. Okay, so party I has secret TI, and that's a secret key of party I. And I want to talk about the expanded secret key, which would be just taking all the secret keys and concatenating them together. Okay, so let me call that the expanded secret key. It somehow belongs to all parties. And our goal will be to take a ciphertext that belongs to party I, just a single party ciphertext, so party 1 encrypts, and somehow convert it into this, into something I'll call it an expanded multi-key ciphertext. Okay, so somehow expand it. So party I ciphertext has this property, C such a TIC is XTG, where X is the encrypted bit. I want to expand it into something that has the exact same format like a GSW ciphertext, but under the expanded key T star. So I want to convert it into ciphertext C star such a T star, C star is XT star. Well, not quite G. Okay, everything blows up, all the dimensions are blowing up, but some sort of an expanded version of G that just looks like this. So I'll call it G star. And you can have the same G star inverse. So the same inverse operation works for G star. So I'm just blowing everything up. So all the dimensions increase. But if I do that, then I can do that for each of the party ciphertexts, convert them into this expanded form, and then they look just like GSW ciphertext, just with bigger dimension. So I can do all the operations, homomorphic operations of the expanded ciphertext, just like we did before. Nothing else changes. So the only question is how to do this expansion, how to take this one party ciphertext and convert it into this expanded form. Okay, good. So let's do this for just 2 parties. It'll be easier, but you'll have to believe me, I'm not cheating. Everything extends naturally to as many parties as you want. Things grow sort of proportionally. Okay, so here we have 2 key pairs of 2 different parties. And so I told you that they should be independently generated. I lied a little, okay? They're going to use some common randomness. Think of it as public parameters. So this matrix B, just a random matrix, they're going to use everyone's going to use the same one. Think of it as like a generator of a DDH group or something. Everyone uses the same one. That's the only coordination.
It's a public parameter of the system.
Public parameter of the system. And uniformly random string. Yeah. So, okay, but they're going to choose this last row individually. So different individual secret keys and individual public keys. Okay, so these are the two properties they satisfy. And now, the party one encryption of a bit X is going to be just like before in GSW. So this is how we did it before. But we're also going to add some extra helper information. I'm going to tell you what that is later. So there'll be something a little more. Okay, but the main thing is the encryption that we had before. And this is the property that we analyzed before. So if you this is how you do decrypt. If you multiply by the secret key of party one, you get this thing. Now let's do something sort of weird. Let's see what happens if you try to decrypt with the secret key of party two. Now this should give you nonsense. You're decrypting with the wrong secret key. It gives you mostly nonsense, but there's some sense to the nonsense. So what does it give you? It gives you, well, we can do it. So C is this like A1R plus XG, right? That's the definition. If you do T2 times A1, okay, so you get negative S2B plus B1. Okay, so you get this thing times R, this randomness R plus XT2G. Now, negative S2B is very close to B2, right? So you get B1 minus B2R plus XT2G. So you get this thing, which is what you wanted. This is what you would get if the ciphertext was actually encrypted under party 2's key. But you get some blinding factor that depends on R and the two public keys. Okay, so you almost get the right thing, but somehow blind it. And of course, it has to be blinded. You shouldn't get the right thing. So this is what we're going to do. We're going to create an expanded ciphertext C star that's going to look like this. It's going to have just C on the diagonal and some matrix D at the top. Again, I'll tell you what D is exactly later, but let's see what property we need from D. Then we'll see how to do the helper information in D. So I want to make sure that, this is the equation I want. I want to make sure that if you decrypt with T star, the concatenated key, you get the right answer, XT star G star, right? So that's the property I want. So if you see what happens, so T star, C star is just T1, T2, C star. So T1 gets multiplied by C over here on the left. So you get T1C on the left, and you get T1D plus T2C on the right. So we analyzed both of these terms. So T1C is just XT1G, and T2C is this thing. So I need to make sure that T1D plus T2C is this. Okay, so here's what I need. I need to make sure that T1D exactly gets rid of this blinding factor that we had here. Okay, so again, just to summarize, my goal here is so there's two things I didn't tell you how to do. I didn't tell you what this helper info is, and I didn't tell you how to create this matrix D such that this holds. Now, I want to emphasize, actually, this is important. This helper information that the party one creates at the beginning, it's totally independent of party two. Party two isn't around during encryption time. Okay, so this helper info doesn't depend on party two. You don't know his public key or anything like that. But over here, when you create D, when you expand the ciphertext, you do know what party two is. So this happens at evaluation time. So here you do know the public key of party two. So again, let me just summarize the goal now that we have here. So given a party one ciphertext and some helper information, we want to find a matrix, and later, so this helper information doesn't depend on this part over here at all. But later, when you get this part, you want to find D such that this holds. Okay, that's our goal. That's our only goal. If we do that, we're done. So, and here's the idea. The helper information is just going to be GSW encryptions of all of these, of the randomness in this ciphertext. So I'm encrypting a ciphertext, the bit I care about, and then I encrypt all the randomness. That's all I'm doing, under my own key, under party one's key. Okay, so that doesn't hurt security. I mean, you're just encrypting the randomness, everything's semantically secure. That's fine. Now, to get this matrix D, we're essentially going to do some sort of a homomorphic computation on this encrypted randomness. So we're going to do a homomorphic computation where on these ciphertexts that encrypts Rij, to get a matrix D, which essentially looks like an encryption of this value, B2 minus B1R. Now I'm cheating a little, like the T star disappeared, the G disappeared. So you're going to have to believe me that this is doable. Let's see. Yeah, I don't think I have enough time to do it. So you'll have to believe me that this is doable, but it really follows the same approach as the standard GSW homomorphic operations. I'm somehow taking the encryption of the randomness R bit by bit and combining them to get this. I need to like cancel out the G, so I'll just multiply by G inverse on the right. Okay. So that's it. That's the whole idea. That's the multi-key FHE. So now let's talk about how to do decryption, distributed decryption of this. So let's again look at the equation. So we have this expanded secret key T star. And if you just wanted to decrypt in a non-distributed way, you could just multiply T star times T star and get, see if this is small or big. If you thought about doing this in a distributed way, yeah.
So you're revealing encryptions of the randomness used to produce the ciphertext, so you don't need a special property of the...
That's right. I don't need any special property. There's no extra secure assumption. This is just secured by the GSW FHE security, which follows from LWE. Yeah. Okay. So if I didn't care about secure decryption, just wanted to decrypt in some way, this is what I do. But you can see, even if we somehow distributed this procedure, this computation, that would be terrible, because just revealing X T star G star, if X is 1, you learn all the secret keys. T star is the concatenation of all the secret keys. And from T star, G star, you can learn everything. So that would reveal a lot of information. We can't do that. So the first step is going to be to somehow sanitize this ciphertext. So we can't just directly decrypt this ciphertext, just even give you the output of this computation. It's too much information. We're going to sanitize. So what does it mean? We're going to just multiply by G star inverse of W, where W is this vector, just zeros and Q over 2 at the end. What does that do? Well, now if you take T star times this vector C, you get T star, C star, G star inverse of W. And essentially, you get this thing times G star inverse of W. So that gives you X T star W. Now, T star, remember, all of the secret keys have a 1 in the last component. So everything will cancel, right? It's just zeros. You'll just get a Q over 2. So you'll just get X times Q over 2. So you don't really learn anything more than just X. Doesn't depend. We got rid of the secret key here.
Is this more generally a deterministic sanitizing procedure for the scheme, for the FHE?
You can call it that, yeah. Yeah, so I'm saying at least now it's okay for me to reveal T star C. Well, even that is a bit problematic because there's some error here, right, that I don't want to reveal. It's not complete randomization because of error, but close enough. Okay, and so now we need to compute this in a distributed way. Let me take this vector C and just write it down this way. So it's an little n times capital N. Capital N is the number of parties vector. I'm just going to write it down this way, where each component sort of corresponds to one party. And then T star C is just the sum of Ti, Ci. So now we can do this in a distributed way. So what's the distributed way? Each party just outputs a partial decryption Ti times Ci. So each party everyone can compute the sanitized ciphertext, a deterministic procedure, and then everyone just takes this component and multiplies it by its own vector, and you can add up these partial decryptions and recover this. It's one extra thing. The partial decryptions, you're going to have to add a little bit of error. And this little bit of error you have to add to drown out whatever error was contained in the original ciphertext, because that could be sensitive information too. Okay, so each party just adds big enough error to drown this out. And here's the security property you get. You can, and it's pretty easy to show, you can simulate one party's partial decryption given just the output X and the secret keys of all the other parties. So you need to sort of know what everything else is. But that says that if everyone else but one party is corrupted, I'm not revealing that one party isn't revealing anything extra about its secret key other than the output of the computation. So you can simulate. So just to summarize, this is the protocol we had. We're going to just plug in the multi-key FHE into this protocol. There's a little bit of a subtlety. So we actually show this protocol is secure for all but one corruptions, if you corrupt everyone but one party. It seems to be the hardest case, but somehow we actually have a hard time showing if you corrupt all but two parties. So we need to do some minor modifications to get that. If some of you are familiar with MPC and maybe we're doing something silly. It really feels like it, but for technical reasons, it really seems like we needed this. The other thing is, so far we only get honest but curious security. If you want to get malicious security, we'll need to add NISIGs everywhere. So in this round, actually, people proved that they did things correctly. Well, in this round, too, you proved that you encrypted correctly. So people proved that they did everything correctly. Usually, to go from semi-honest to malicious, you also need to do coin flipping, which would introduce extra rounds. Here, you don't need to do that. It's pretty easy to see that if people use bad randomness, so choose their public key, secret keys badly, they're only hurting themselves, not hurting anyone else. Okay, and a couple of open questions. So one is, can we get rid of the common random string in the honest but curious setting? So we need it because we need these common parameters that everyone uses to choose their key pairs. Can we get rid of that? I don't know how, but it'd be interesting. And the other question...
You can't get rid of it in the malicious setting?
Even in the semi-honest, I don't know how to get rid of it. Yes, it is. There's a lower bound of 5 rounds. Yes. Because zero knowledge. Zero.
The lower bound is for black box construction.
Okay. So, no, but as far as I understand, you can't do just zero knowledge in 2 rounds, right? You cannot do zero knowledge proofs in 2 rounds. Zero smaller. Oh, okay, maybe unlikely. So, all right, I'll leave it at unlikely. And the other question is, can we get 2 or 3 rounds under different assumptions, maybe just oblivious transfers? There really is, or maybe it's also unlikely there's some lower bound, but that would be interesting. So those are the 2 main questions I think are interesting. Okay, thank you.
Yeah. So in the intro-based scheme, the multi-key, they're generating... Okay, here's my question. I want to have a multi-key scheme. Do I have to know in advance everybody who's going to be in the system? No.
No.
So that's a feature that you have that they don't have.
They don't need who needs to be. They don't need to know who needs to use the system. They need to know how many people will be in the system. They need to just know a bound on the at encryption time. You need to know how many parties, a maximal number, and the number of parties you'll support. We don't.
You don't.
Yeah.
So in other words, it's sort of flexible. So you've got a scheme, and then many more people want to join in a multi-key scheme, and they come as go along. You can do that.
That's right. That's the case for the clear and McGoldrick and the simplified version we give. We don't need to know the bound. The disadvantage over Entru is that we need the common parameters. They didn't actually. They didn't need any common parameters. This matrix B. So trade-off. Yeah. That's right. Just a random string. Yeah. Nothing else. No, that's right. In the malicious case, also the CRs of the NISIG, but that could also be a random string.
Any other questions? All right, let's thank you.